much. So it's it's a pleasure to be here. So yeah, I'm going to talk about using energy as a witness of non-locality and in many body spin systems. And well, this is joint work with these other people. So there is Remik here, who was very kind to invite me, and other collaborators, so Maciek and Tony, that are at ICFO. Maciek was my PhD supervisor, Gemma, that is now in Innsbruck, and Ignacio, who is now my boss in the Max Planck Institute of Quantum Optics. The paper, you can find it on the archive, and well, this is the outline of the talk that I'm going to present here. So first I will motivate the problem that we want to investigate. I will present what is the general idea of our method. Then there are, well, one has to do a quantum optimization, so I will discuss the details on that. Then I will say how one relates Hamiltonian with the Bell inequality to study the non-locality in these systems. Then one has to do a classical optimization to know the so-called classical bound of the Bell inequality. We'll discuss what happens if there are symmetries in the system, such as translational invariance, and then I will present some examples. And then I will conclude and say what are the open problems. Okay, so I think that the audience here comes from very different fields, so maybe a good way to motivate why we want to study non-local correlations and Bell non-locality is what now in the field of quantum information, kind of the trend is this device-independent approach. But I think that a nice way to present this is just as telling a story, right? So if one thinks now of the most mature quantum technology in the market, probably would say it's quantum key distribution, right? Because there are many companies that sell these systems and so, right? And there have been some amazing experimental records in achieving these things, right? And well, if one wonders why people claimed that this is more secure than in classical cryptography or so, right? Well, one goes to the theory, and in the theory, when you want to make a security proof, right, there are assumptions. So, for instance, an assumption would be that your quantum particles are described in a Hilbert space of dimension 2, let's say, right? There could be spin 1/2 particles, so they can have 2 states. But when you go and you open the box and you see the implementation, then you see that this does not look like C2. Yeah, the Hilbert space of this, maybe this is oversimplified, right? And well, of course, then there is a mismatch, right, between the theory and the implementation. And this means that sooner or later, sooner rather than later, someone will exploit these loopholes in the implementation and exploit the fact that here this is not C2, and here we will have the quantum hacker, somebody that will compromise the security of these systems, right? That people thought that because they read the proof and they said, okay, this is more secure than other things, right? And then, well, I mean, this was published in this paper in 2010, and this kind of changed a bit the way that people were looking at these problems. Because, okay, now if there is this mismatch, then the only way out is to make no assumption about the internal working of the devices, right? So I will have what is a very complex device, but I will not care at all how it works inside, right? So I will.
The side of this is that hackers now would have to learn quantum mechanics.
Yes, well, I mean, yeah, here the hackers knew quantum mechanics and they exploited that, right? And now I want that even if the hackers know quantum mechanics, then they cannot do anything, right? So the way that I do it is by treating my device as a black box that I don't care what happens inside, only that it has some input that will select what I'm going to measure. Although I don't know what exactly is the measurement, I will just choose one measurement, and then it will have some light bulbs here that will click whenever I perform a measurement, right? And then this is the the setting, right, in which one studies this non-local correlation. So instead of looking at the Hilbert space, now one looks at the correlations that are produced by the experiment, right? So by looking at the correlations, I'm not assuming even that there is quantum mechanics at hand here, right? So the relevant parameters of my experiment are the number of inputs and the number of outputs. Okay, and then, well, the relevant question here is if the observed statistics are non-local. I'm going to precisely define that in the coming slides. Okay, so guys, so Bell correlations are a resource for these device-independent quantum information tasks, right? And the fact that you have less assumptions, like the Hilbert space and so, means that you will have more security, right? So there is no Hilbert space. Black box devices can be untrusted, right? I mean, you can even buy your devices from an adversary and it will be okay, right? And also, I mean, well, I think that one has to mention that recently some of these loophole-free Bell tests have already been performed, and these were 3 remarkable experiments. So showing that already the technology to show that non-local correlations are there without ifs, let's say, is present, right? And well, to show some examples, quantum key distribution, randomness expansions, randomness amplification, self-testing, and so are the typical problems in which one can apply these non-local correlations, right? And well, of course, as Bell correlations are stronger than entanglement, this is just a fact, right? If you have Bell correlations, then you must, if you have a quantum system, right, then the system must be entangled. Otherwise, there is no way to reveal these correlations, right? This means that it's also more difficult and more demanding to show in terms of technology. Okay, so this is more or less what Bell correlations are used for. And in this talk, okay, we want to explore, so what can we learn in many body systems from detecting these correlations, okay? So why would we try to study them in the many body regime? Or, well, I will start by saying why people have not studied this yet, right? And there are 3 reasons for that. First of all, mathematically, it's a very, very complex problem to decide whether a set of correlations is non-local in a many-body system, because the description of these correlations will grow exponentially with the number of particles, right? So it's a bit like the growth of the Hilbert space. As I said, this is going to be experimentally more demanding to show these correlations. Yeah, exactly. And well, recently also with Remick and collaborators at ICFO, we showed that in permutational invariant systems, this can be revealed. So and now the record is 500,000 atoms, and well, people have done this in Bose-Einstein condensation. I mean, this experiment is for roughly 500 atoms, and so this was remarkable because the current record was about 14 particles or so, right? And then, well, with these tools, we allowed to go much further in investigating this question. And well, in this talk, I will not focus on permutational invariant systems, but in something different. So spin systems in one spatial dimension. Okay, so let me say what non-local correlations are, or what I mean by non-local correlations. So I will have a group of parties, Alice, Bob, Charlie, right? And the experiment is as follows. So each of these parties has an input, x1, x2, x3, right? And this has a finite set of values. So you can imagine that they push a button in their black box, right? And they don't know what this button does, but they push a button, and then they get an outcome, right? And then, well, Alice selects input x1, and then she will get an outcome a1. And Bob does the same, and Charlie does the same. During the experiment, of course, they are not allowed to communicate, right? And you have to imagine them to be in space-like separated laboratories. So they do this lots of times, and at the end of the day, they can estimate this conditional probability. So the probability of having a set of outcomes, given that they have pressed a set of inputs.
You don't assume anything about the communication between them. There must be some link.
They are allowed, prior to the experiment, to communicate whatever they want. I mean, they can agree on following a strategy, let's say.
No,
if they
during the experiment, there is no connection?
No, there is no connection. Of course, I'm thinking here that they will share an entangled system, right? So they're going to have non-classical correlations. But the crucial part is that, for instance, Bob cannot know what is the measurement that Alice is performing, right? Or the rest of the parties.
Before an experiment,
Yes.
prevents them from setting up a system that whatever happens, they always press one button.
No.
And then this condition probability is...
Well, then you could not estimate it because you would lack some information, right? So the thing is that, of course, they choose.
They act at some sense at random.
Yeah, they have to choose randomly their inputs.
So,
Yes.
So they cannot communicate. In that sense, they cannot communicate.
Yeah, they can.
System must prevent conspiracy.
Yeah, I mean the input that you are using, the others cannot know it. That's the rule.
Yeah, but
Yeah,
I
that's-
can agree with Alice, can agree with Bob and whoever is it, Charlie.
Okay.
That whatever happened, that always press the upper left button. And then this conditional probability, something will come out from these boxes, right?
Yes,
Yes, but-
so there is some condition of this probability.
Yeah, but that,
So this situation is very well described by such a setup, okay? Then the probability has some concrete values, okay?
Yeah.
And that's true.
Yeah, I mean, if you press an input less often, right, you will have to repeat the experiment many more times to achieve statistical significance to define that.
A priori they measure the same. They somehow consider they agree to measure all the
then
same.
assumes that the black box always answers the same way you press the same button.
Oh.
No.
This is obviously even not true in classical mechanics.
Well, I don't know. Thus, in my coffee machine, I press the button espresso, almost always.
Are you sure? Oh, you're a lucky man.
When something else come out, I throw out the machine.
You're a lucky man.
Yeah.
Okay, let's proceed.
No, well, yeah. I mean, the outcomes can be probabilistic. There is no problem with that. I mean, formally, the requirement is that the inputs are uncorrelated from the state of the system. That's the only thing that is required. Okay. Well, so now we have these conditional probabilities, right? And then this is a set of many numbers. So I think that the easiest way is to visualize that geometrically, right? So I can arrange them. I can arrange them in a vector, right? So I just consider all this, and then this vector will correspond to a point in in a very large affine space. And now the question here is, well, according to the physical theory that I believe that these people are constrained with, right, or according to my physical model, then this point can take some values and cannot take some other values, right? So if I consider a model of local hidden variables, then this has a, let's say, feasibility region. So it has a subset of this space that is compatible with this model. And this model and this subset is a polytope, meaning that it's a bounded convex set with a finite number of extreme points, right? So it looks roughly like that. This would be a cartoon picture. And what is relevant, right? I mean, this is Bell's theorem, is that quantum correlations, quantum mechanics, are strictly larger than this set, right? So I mean, by performing some measurements on some entangled particles, you can get correlations that are not compatible with this local hidden variable model description, right? So I mean, if you take maximally entangled state with two parties, right, and you make these measurements, and you would be outside, and so. And more generally, I mean, people can think that's also a very interesting problem. It's that if one assumes this no signaling principle, so just the fact that when Charlie presses a button, this cannot be detected by Alice or Bob which button he has pressed, right? So Charlie cannot communicate information, cannot signal instantaneously information, right? Because okay, the only way that Charlie has to transmit information is by choosing a different input to their experiment. So if all the marginals are the same regardless of the inputs of the other parties, right, then this is the no signaling principle, and this also forms a polytope, but it's strictly larger than the set of quantum correlations. So here the vertices of this local polytope are of interest, and this corresponds to the cases in which the black boxes behave deterministically. Right? So every point here would be when so I color that in the same way. So the output of Charlie's box, right, would be, for instance, I will always output 0, or I will always output the same as the input, or the contrary of the input, right, or always 1, or so, right. So this would be the deterministic program for Charlie, and the same for Alice, and the same for Bob. So this would describe the vertices of this polytope. So now, how do I access all the region inside? And then, well, this is just by mixing these strategies, right? And this is because I said that the parties are allowed to meet in advance and agree on a strategy, right? They can, for instance, this would correspond to the hidden variable in the theory, right? So they are going to have some shared randomness that is going to be this lambda, and this lambda is going to say, okay, in the first round of the experiment, we're going to follow strategy 1, right? On the second, strategy 3. The third one, strategy 1 again, right? And then they're going to produce these correlations. And then you see that this object is going to be the mixture, right, according to this probability distribution of these vertices. So you can access, because this mixture has to be a complex combination, you can access any point inside. And then, well, what is a Bell inequality? Then Bell inequality is just a witness for this local polytope. Okay, so if there are any questions, but yeah, feel free to ask. So what is the idea that we're going to follow in our construction? So in our construction, we start with a Hamiltonian H, right, energy operator of a quantum system, right? So this is at the level of states. This is not at the level of correlations yet, right? And we want to see if the ground state of this Hamiltonian, right? So we're going to measure the ground state energy, and we want to see if that ground state has correlations that violate a Bell inequality. And well, to violate a Bell inequality, okay, well, sorry, I forgot to say that typical tools to find this ground state energy, depending on the system, you can use the Jordan-Wigner transformation, or matrix product states, or the MRG. I mean, some numerical methods that work very well for 1D systems, right? So as I was saying, so one has to relate this Hilbert space now to the space of correlations. And well, when one has a Bell inequality, and then you want to probe it with quantum mechanics, right? You need to put quantum observables there, and then you get what is called the Bell operator. The Bell operator is just the Bell inequality when you put the quantum observables in it, right? And then you minimize the expectation value of this Bell operator, and then you would see that, I mean, if this Bell operator, you manage to construct it in the same way as the Hamiltonian of your system, right? Then the optimal quantum value for this Bell operator is just the ground state energy of the system. Okay, so now one has to find a Bell inequality, let's say, right, from the Hamiltonian. So it means that I'm given the Hamiltonian, and I have to pick appropriate inequality coefficient, right? So I have to make a linear combination of these conditional probabilities, right, to get this inequality in a way that matches. And also, I mean, the method can be seen the other way around. So if you give me a Bell inequality, I can try to find suitable observables such that the Bell operator will correspond to some Hamiltonian of interest, right? And then, I mean, it works in both ways. If I'm given a Bell inequality, then I have a classical optimization to do to say that it's, to certify that it's a valid Bell inequality. And it means that I have to optimize it over all the local hidden variable models, right? I have to optimize over this local polytope of correlations, and I have to find, the offset that one has to add to have a valid Bell inequality. So this is the classical bound. And then, well, when I will introduce what is called dynamic programming. So this is a technique to find this classical bound efficiently for 1D systems, right? In general, it's one requires optimization of an exponential number of constraints in a linear program to find this classical bound. So it's very hard in general, but for these systems, we're going to show that it can be done very efficiently. And then simply by comparing these two values, if one is greater than the other, then you will have non-local correlations in your system. So on top of that, if one has a symmetry that is natural in 1D systems, such as translational invariance, then we can hope for something better, right? So here in the quantum part, we can have analytical expressions for the ground state energy, right, and the quantum value. And here we can have an exponential speed up in finding this classical bound.
But you have to do something to this ground state to have any phenomena, because ground state is just dead. It's there, sitting, and nothing happens.
Yes, I prepare the ground state, right? I would measure its energy, and this will give me what would be
to measure energy, you have to do something to the ground state. That means you go from ground state to other states. Ground state does not have to couple it. You must couple it. You must disturb the ground state.
Well, let me phrase it maybe this way. So if I prepare a state of sufficiently low energy,
well, prepare it means you wait infinitely long.
No, I say sufficiently low energy. It can be a thermal state. It can have noise.
Wait.
Yeah.
There are physical system, particular spin ones, for which close to the ground state there are infinite number of energy states which are very tiny little bit.
Yeah, it can be very close.
So when you prepare them, how you know in which state?
Yeah. Okay. So let me say. Here, the optimal choice would be the ground state energy, the state of minimal energy, right, in the paper. But if you...
But there is no experiment. If the ground state is there, the
system
well,
goes into ground state, that's over.
Yeah.
I can give you a Hamiltonian, right, and
so,
a spin Hamiltonian, and from this you can construct the quantum state that will minimize its energy. This we agree, or?
Yeah, but you have to compare this ground state with some other states to have information about the system.
On a paper, you can calculate.
Yeah. Okay. In a real experiment, you would have noise and you would have a thermal state.
If you go late into the DM and the Magma with the laboratory, he gives you an icing model.
Let's wait until we see how it's done.
Well, in any case, let me maybe just say that if I have a thermal state of sufficiently low energy, then this would be also working. Right?
Not quite, because then you have to couple this state.
There are two issues I think which are mixed here. First one is that whether you can achieve in a finite time some stationary state, whether it is thermal state or ground state, is a problem. And the second thing is to which state you make this measurement. And this state, these measurements are made in ground state. So what? You can assume that there is some state and make all the measurements of many observables in this state. So what is the problem that this is a ground state? In ground state you can measure whatever you want. Spin, you can measure momentum, you can measure velocity, you can measure whatever you want.
But measuring means disturbing the ground state.
As always.
Yes.
Dependently whether it is ground state or not a ground state. Yes. In excited state, but in excited state would be maybe worse, I would say.
Okay, maybe will be clearer in the coming slides. Okay, so let me present the setting, right? So the systems that we are going to work with. So as I said, spin will have Hamiltonians and particles in one spatial dimension. So you can imagine them like this. Right? One can have open or periodic boundary conditions. This is not so important in the end. The method works in both cases. what is going to be important is that the interactions in this Hamiltonian are short range. Okay, so I will denote by this capital R how many neighbors your Hamiltonian affects.
So that's the Ising model.
Yeah, you can imagine, for instance, an Ising model. So
if they are short range interaction, or is spin one after what else?
well, it can be XXZ model, or it can be Heisenberg, right? I mean, just yeah. So I'm thinking here of a Hamiltonian of this form, right? I mean, I have some sigma z's, and I have these string operators that are going to be so chains of x or y, right? Some z's and x or y. This is a bit maybe unnatural, but I'm going to use these Hamiltonians for the sake of argumentation, because this can be diagonalized exactly with the Jordan-Wigner transformation, right? So
that's a fancy way of saying that you permitted 3-body interactions, 4-body interactions.
yeah, but up to R, right?
Yeah,
up to R.
A certain range.
Yeah, up to a certain range. I mean, the method will work if here you put any chain of spin operators of Pauli matrices. But to use the Jordan-Wigner and have analytical results, and so I will constrain myself to this. So, yes, yeah.
In this fancy way, do you permit the spin number 1 interact directly with the spin number R, or there is a chain in between?
There is here there is going to be a chain in what I'm going to present here. But the method will also work if you have only just 2-body interaction between spin 1 and spin R.
This one dimension, that if you have 2 spin interactions,
Yes.
then it's the same as a 1 spin. It's in every book a sigma z at the point I plus times sigma z in the point I plus 1 by what is called in the textbook sigma tau transformation is transformed into this free spin system.
Okay.
So I'm asking whether this Hamiltonian by the same trick cannot be reduced, because in the one-dimensional Ising
But it's so,
Well, we
general,
don't-
it's so
don't know.
general that
yeah, I'm asking if I have this so many spins multiplied by each other, then each 2 of them I can replace by the 1 spin, and then I continue doing this, and eventually I will end up with the first term.
But you will have also x's and y's and this and
Now I will
this.
have a constant.
Okay. Well, we did not check
Take
this.
a simple example where you have a 2-spin interaction. Okay, that is an example of your Hamiltonian. Okay?
Okay.
Then sigma z at the point I times sigma z at the point I plus 1
Yeah.
is a sigma z.
But this term will not appear in my Hamiltonian here.
It appears in the first term.
No, there is only sigma z at site I. This is not multiplied by
Yeah,
at
because
any
I
other.
can relabel I times I plus 1 in the, is this finite chain or infinite chain?
No, this is finite chain.
And what are the boundary conditions?
Well, you can leave them open or periodic as you wish.
If they are periodic, then this transformation also works, and you have a free spin system.
Yeah. Well, okay. Yeah. Also with the
Written in every textbook. That is how you solve Ising model in the 1-dimension.
Yeah, I mean, we consider this because, I mean, it can be mapped to a free fermion system, and then we can find the ground state energy efficiently, let's say, right? I mean, so one of the... yes, for this example here, it is a free system. The method will also work if you don't have a free system, but I think it's, I mean, it's easier to see afterwards. Okay, so yeah, by doing the Jordan-Wigner transformation, you can exactly diagonalize this, right? So one can introduce these Majorana fermions that satisfy this anti-commutation relation, and well, you would map these chains of spin operators to these fermions, and then every Hamiltonian of this form becomes quadratic, right? So this is just a transformation at the mathematical level, right? And what this allows us is to find the ground state energy easily. So this matrix here of coefficients is real antisymmetric. Well, I don't know if people are familiar with this transformation or not. Maybe I will go faster if this is the case. And then one performs some Williamson eigen decomposition of this matrix of coefficients. So every antisymmetric matrix has a decomposition of this form. So we block diagonalizes into these 2 times 2 blocks with an orthogonal transformation. And then, well, this what does, it mapped your original family of Majorana fermions to a new family of Majorana fermions. Then your Hamiltonian looks like this way, and these operators are mutually commuting, right? So they have a common eigenbasis. So it means that they have a common, eigenstates of this Hamiltonian. You can construct them by choosing the eigenvalues of each of these operators. So you will have some energy levels, right? Here there are as many as n, right? So this is a crucial part here. And if you separate them into the positive ones and the negative ones, then you find the ground state energy just by optimizing this function, right? So these observables can have eigenvalues plus minus 1, then by choosing the sign appropriately, right? So this would be negative sign and this would be positive sign, then you have minimized this sum, and then this is what is the ground state energy of the system. There are some subtleties here, like the parity that can impose a super selection rule. And so I mean the sign of this transformation, if it's direct orthogonal or inverse, this will flip your parity, and so. But well, I will not go into these details.
Yeah. Anyway defined up to a constant. So why don't you call epsilon naught the ground state, the lowest state?
No, this is not the. These are not eigenstates of the Hamiltonian.
These are not eigenstates.
No, every sum of them with plus minus signs, right? Here there are n terms, and there should be 2 to the n, right? And this is exactly what you get here by making all the combinations of plus minus 1. Right. So these are Hamiltonians.
It's really the lowest energy state, the lowest eigenvalue.
Yeah. So when you pick these signs to be negative and this, these ones to be with positive sign and this with negative sign, right? Then you have the ground state energy. So we picked these Hamiltonians because we can do this trick and find the.
Hamiltonian should define the ground state without any arbitrariness.
No, here there is no arbitrariness, right?
No, what about these? How do you find the sign of SK?
Just by looking at the sign of the epsilon. Right. So here I get the epsilons by this the composition, and then while I have this list of numbers and I just do this thing. Okay. So this is an easy way to do the quantum optimization that is needed in our problem. So now let's see how from this we can construct a Bell inequality, right? Because this is more or less known, and the new thing will be how to make a Bell inequality. So we want our Bell operator to be of this form, right? So this B is the Bell operator, H is the original Hamiltonian, and then there will be this classical bound. That is the optimization over all the local models. So I will shift the Hamiltonian by the classical bound, right? And I want my Bell operator to look like this. So it means that here Alice has some inputs that defines some different measurements, and she will get some outputs, right? So I'm in spin 1/2, so I'm going to naturally put that Alice can choose 2 different outputs, and what we can do is to take m measurements in the xy plane and an extra measurement in the z direction, right? To have this string operator structure that was needed in the first place, right? So she will measure something in the z direction and then as many measurements as you wish in the xy plane in the block sphere, right? And then this Hamiltonian, I can naturally assign to it a Bell inequality of this form, right? So this would be, I will label my measurements from 0 to m, right? So there are m plus 1, so the last one is going to be the sigma z's, right? And then, here in this correlator of many parties, right? On one side I'm going to have k, that is some observable here, some observable here, and in the middle I will have the z's. So it just, when you do the substitution, you would recover a Hamiltonian of the original form. So how do we find the classical bound, right? This is the classical optimization that one has to do. So we have an inequality of this form. We want to compute this minimum over all the local hidden variable models. So we have to optimize over this polytope, right? And then, well, there is a result that is called Fine's theorem, or just can think it in a more general way, fundamental theorem of linear programming that tells you how you want to optimize a linear function over a polytope, then the optimum is going to happen at one of the vertices of the polytope, right? And this is what Fine's theorem tells you in the context of non-local correlation, so that the optimum is going to be in one local deterministic strategy. So it means that by going through all the local deterministic strategies here, then you have made now this optimization over an infinite set to an optimization over a finite set, right? So you just check all the vertices and you have done this optimization. So how hard is it to check all the vertices? Well, imagine that every party can choose different measurements, right? And then I will have a set of parties, right? Alice, Bob, Charlie, Donald, and so on. And well, for each party and each measurement, they can have an outcome. So either red or black, for instance, right? So Alice can have this deterministic strategy, for instance, right? And Bob can have a different one, and Charlie, and so on, right? So I can think of a local deterministic strategy as a table of this form. So how many elements do we have here? Well, we have 2 to the number of measurements to the number of outcomes, vertices, right? So there is an exponential number of vertices. So in general, this is a very, very hard problem, right? But for our Bell inequalities, because they have this kind of one-dimensional structure, one can do much better. So it's not necessary to go through all of these 2 to the mn vertices, but just one can really build this table and find the optimal strategy with this dynamic programming. So with this procedure that I'm going to describe here. So yeah, this is what I said. So what do you need for this dynamic programming? So you need kind of a recurrence relation that you can compute and store subsolutions, and you can order them. Then you put it in this machine, and what you will get is polynomial scaling, right? You will construct one optimal solution, so one of these vertices at the boundary. So this is much better than going through all of them. And well, for those of you that work in numerics, probably you know that already. But this is a very versatile programming technique. So if you go to to some website in which they do coding competitions, you see how many problems fall into this category, right? And this is the 3rd most common. So I mean, you can really apply it to many areas. So in our problem, this dynamic programming goes as follows. So we would have a Bell inequality that you can think of as a sum of smaller Bell inequalities, right? Because the interactions are short-ranged. And then the optimization will look like that, okay? So I will be at this point. So this would index the parties, it would index the measurements, and I would have, at some point, part of the optimal strategy built already, right? Then I want to find, okay, for the next party, what is the optimum that they have to do. Because of this short range of the inequality, there are going to be parties that actually are so far away that I do not care about what happens here, right? Because the range of the inequality is finite. Therefore, whatever I put here cannot influence the parties that are sufficiently far away. And well, finally, the problem would be with the parties that you have inside your range, right? So in these green squares would be the parties that I'm trying to optimize, but this optimization will depend on the parties that are already after them, right? Because to compute this, the correlators here in this Bell inequality. So if I am optimizing B, I need to know what is going to happen in C, right? Otherwise, I cannot optimize the value of the function here, right? And well, this motivates to define this kind of recurrence relation. So because Charlie can only have a finite number of values, right? Because here I can only paint this in a finite number of ways. Well, I can compute all of them, right? And then this will define me this function. So I will have this function that will depend on the immediate parties after party I, right? That will be the minimum of the same function before. So this will be this red square, right? Plus the interactions of the inequality. And well, once I have this function here, you see that I can go one step further. And with this, I can advance and find, an optimal strategy for all the parties. So here, the classical bound, you find it by construction as the end step of this optimization. And what I think is remarkable here is that the overall complexity of this is linear with the number of parties, so it's not exponential, right? And in general, one would have an exponential number of steps to do here, but because of the form of the inequality, you are able to do it just with a linear number of steps. Yes?
So
Yeah.
say that this procedure is something like a quantum version of the transfer function.
Well, here there is nothing quantum going on, right? I mean, it's
If that was not a quantum moment, you would be exactly solvable for whatever problem you want without doing anything.
yeah.
Because the one-dimensional spin model.
Yeah, but this is a Bell inequality. So this is in terms of correlations.
So that's
So when I'm considering correlations, I'm not. I do not need to assume quantum mechanics or anything. It's just within the theory of local models, right? And then how you obtain these correlations is not important here. So this optimization you can do it without assuming anything quantum. So here, when you have this symmetry, maybe it would be more clear, because now you can have an exponential speed up on top of that if you have translational invariance, right? So now a translational invariant Bell inequality will look like this, right? And then you would have the same inequality at every link.
And you have to have infinite chain to have translation invariance.
No, well, I mean, I put periodic boundary conditions for yes. And then the idea would be, so I can think of this problem as minimizing the following function, right? I have a function f0 that would correspond to whatever is inequality at each link, and this would depend on the variables xj and xj plus 1, right? So the neighbors. And I want to minimize this over all the possible values that all the parties can have. So what I can do, because now the function is the same, I can eliminate half of the variables at every step. Right? I can define a function, for instance, between a and c. Right? This would depend on the value at a and the value at c. That would be the minimum over all the values that b can take. Right? So this I can compute it for every value that a and c have. Right? And by this I have eliminated b. And well, doing the same between c and e, I eliminate d. Right? So by computing this function, I have eliminated half of the variables. Right? So I would start with a chain like this, for instance, and then all the purple sides I eliminate by doing this iteration. Then all the blue sides that well, more or less look the same, sorry for the color, I would eliminate them as another iteration, right? And so this gives an exponential speed up. Of course, not everything is a power of 2, so there are going to remain some residues here. But now, I mean, the amount of remaining parties is just log n, right? So now I can do the previous procedure. And so now between these two that have a different function, I can eliminate this, right? And then I eliminate, so now I proceed linearly, as you see. But this linear scaling is on a logarithmic number of parties, so means that, overall, you have the classical bound, you find it in order of log n steps, right? So it's a doubly exponential speed up with respect to the general case. Okay, so yeah, this maybe it's a bit too technical. So this can be also applied if the inequality has range greater than 1. Okay, I'm a bit tight on time, so I will not discuss this, but you can believe me that well, this can also work with when r is greater than 1. Okay, so now let me go back to the quantum optimization. And so if I have a translational invariant Hamiltonian of that form, right, that would come from one of these translational invariant inequalities, right, then it would mean that these weights do not depend on I, right, and then this matrix of coefficients of in which I applied this Williams sum decomposition now has more properties, right? So now it's no longer. I mean, it's still real and antisymmetric, but on top of that, it's block circulant, right? And so roughly it would look like this, right? These are going to be 2 times 2 blocks given by these fermions, right? But every block is going to be the same on each diagonal, right? And then because of the interaction range, if you have periodic boundary conditions, you're having to have something like that. If the fermion system has parity -1, right? If not, it's going to be a bit more involved. But so the idea here is that block equivalent matrices you diagonalizing with a discrete Fourier transform, right? So you know that orthogonal transformation now it's just a Fourier transform, so you don't have to find it numerically, right? So yeah, what I said about the parity, then I mean you would have something that would look like this. So this is no longer circulant, but you can kind of expand it and make it circulant. So you take a big one, a big H matrix. This does not change the rank, right? Because this preserves the rank of H, and then this big one is circulant, and then you can apply this. Okay, so the important part here is that this Williams sum eigenvalues, so these energy levels, now you can find analytically. You just use this and you make this substitution in terms of the interactions of your Hamiltonian, and you find the energy levels, right? So there is no need to do any diagonalization or anything for any n, because you just plug it in, right, and you get the result. So now I'm going to maybe illustrate what I said with some examples, so how our method is applied in practice. And yeah.
What you said would apply to any state. You don't even need the Hamiltonian. You just write down a state of the system and then apply these methods. Where does the Hamiltonian enter?
Well, if the Hamiltonian is very large, right? To write the state can be already
But you can just
no
write
problem.
the state.
Well, with exponentially many terms, right? If it's a generic state,
But
that's
pick one. You just take one state.
yes.
Then
Okay.
you apply your
Okay.
procedure to
So I have to take the expected value of the energy of that state. This is where the Hamiltonian comes into play, right? So this is my observable.
Yes.
And well, this is why I need the Hamiltonian, right? I mean,
you can say my state is the ground state of some Hamiltonian.
yeah, exactly. And then I mean, I have to compare. So here, if I go to this polytope, just a second. Exactly. Here. So here I would have some statistics, right, from my Bell inequality, and I have found this beta c. This is the classical bound. So this is my witness for non-locality. Now I have to compute those statistics with the quantum state, right, the ground state, if you want, or whatever. So I have to measure the
any state. Suppose you have a state.
or any state, the state that I want to measure.
Then you can construct this figure.
Yeah, but I have to estimate the energy of that state, right? Because I mean, the Bell operator here, when I put quantum observables in our method is built in a way that what you will get is the Hamiltonian plus an offset that is a classical bound, right? So I mean, to measure the Bell operator is the same as measuring the Hamiltonian. Yes, I mean, taking the expected value of the Hamiltonian on that state. But we can discuss later if you want. Let me go back. So yeah, examples. So the first approach that one uses in non-locality, is to compute this polytope of non-local correlations. And then, well, this is a very costly computational approach. And well, but this is a natural one, right? So the problem is that finding all Bell inequalities here in 2 dimensions looks very simple, but it's very, very hard in practice because this is a problem whose complexity grows doubly exponentially with the number of parties, right? So the dimension of this polytope would be this, right? If this is the number of parties, measurements, and outcomes that you have in your Bell experiment, the number of vertices is also exponential, as I said, right? So it looks more or less like this rather than something simple. And then, I mean, you can make some extrapolation about how long it will take for different number of parties, right? For 2 parties, you compute it in milliseconds. For 3, you would take 5 minutes on the computer. And then, according to this formula, it would take 10 to the 67 years already for 4 parties, right? And if we want to go to the many-body regime, right, we have a number that doesn't even depend on the time scale that you want to measure it, right? So it's not a very good approach, right? So even by putting symmetries that simplify the structure of this polytope, and so what we can do is, this is a simplification of the structure. We can go up to 8 parties. This is the best that we can do. So it's not really many-body, right? So this polytope approach, well, I mean, here you have an example that, I mean, the classical bound would give 32, and the quantum value would be something slightly larger, right? So you have a small violation. So it's not a practical approach to follow this polytope. So we have to do something a bit more involved. So we are going to start by building a quasi-translational invariant class of Hamiltonians and see how it behaves. So I'm going to add a parameter epsilon. I'm going to consider a large number of parties. And here, so if you take, for instance, a Bell inequality that is maximally violated by the maximally entangled state, right? So a 2-body Bell inequality, maximally violated by the maximally entangled state, so CHSH for people that are in the field. And I sum it here with weight 1 plus epsilon, right? And then the same inequality with weight 1 minus epsilon, 1 plus epsilon, and so, right? I can keep building this for as long as I want. Right, and this would be this Bryson-Caves inequality for many measurements. It looks like this. Well, this is not so important, the form. So the point here is that you would always detect non-local correlations when epsilon is plus minus 1, right? Because if this is plus minus 1, then half of the links here will disappear. And then, well, I mean, the best state to prepare is on the links that remain, just maximally entangled states. But now I can, with our method, vary this epsilon and see what would happen. What happens is that at epsilon equals 0, so every inequality here contributes with the same weight. And then there is a phenomenon that is called monogamy of correlations. That is the one that dominates in this case. Right, so you know that like in some entangled systems, I mean, if you have 3 qubits, you can, if Alice and Bob are more entangled, then Alice and Charlie cannot be so more entangled, right? So there is a trade-off. So the same happens for these inequalities here. So it means that when epsilon is 0, the correlations cannot be non-local, right? Because they would violate this monogamy of correlations. So this automatically implies by continuity that there must be some critical epsilon in which, well, there is a range of epsilon in which your model is non-local. So because the Bell operator is, I mean, you can express it like this, right? This is kind of a XX, I mean, like an XY Hamiltonian, right? So it falls into the category of Hamiltonians that we know how to solve, right? And then we can just take this, the limit when n goes to infinite, and plot something like that, right? So this would be epsilon here. This thing that is not C infinite would be the classical bound, right? So it means that here at epsilon equal 1, what you do is you change your deterministic strategy, right? So it behaves differently. And then this curved line would be the ground state energy of your Hamiltonian. So you see here, as I said, at epsilon equal 1, you always have non-locality, right? And this would be the amount of violation. And then, well, there is this interval in which you detect the non-locality of this model. Yes, everything here can be computed analytically, and moreover, you can also see what happens to that interval if you change the number of measurements. And well, actually, it looks like having 2 measurements is the best choice here. But I mean, we did not know it until we computed it. Yes, one can complain here that okay, this I call it quasi-translational invariant, so it's not very translational invariant, right? I mean, it cannot be just the same number everywhere because of the monogamy of correlations that I told you. But following this idea, now I can put probability distribution instead of this deterministic function here, and I would have something in the spirit of a spin glass. Okay, it is not a spin glass, but it's on that spirit, right? So I would put these weights at random, and then my Hamiltonian would look like this, where this I took a Gaussian variable, right? And then for, I don't know, 100 spins and making the average over 1,000 realizations, you have the parameter region of your model, right? In terms of the mean and the variance of your probability distribution, that looks like this, right? So this would be the quantum over the classical bound. So when this number is greater than 1, it would be in a non-local region, right? The intuition here is that, okay, if I don't have any offset, right, and these weights are just centered at 0, just statistically, some of them are going to be of greater magnitude and some of them are going to be of a smaller magnitude, right? And then the weights that contribute the most, then it's better to put something more entangled there that would violate more the Bell inequality and kind of disregard, you know, the other. So this is what the system does when you cool it down, right? And here in that region, I mean, if the offset is very large, right? Even if you have small noise, right? Monogamy dominates because the weights are too similar, right? And then there is no room to violate the corresponding Bell inequality. Okay, so this can be generalized, right? Up to now, I mean, now this talk I have considered Hamiltonians that are solved with this Jordan-Wigner transformation, but now if you look at the tools that I have used, so if you see that it's not necessary to assume that. I mean, if you can somehow access the ground state energy, right, or certify that there exist states with low enough energy, right? This is enough for my method because I only need to compare that value to the classical bound, right? So I mean, when can one do this? If I have speed system, of course, right? Short range interactions. This is necessary to find the classical bound efficiently, right? So I think it's. I mean, I find it at least curious, right, that the short range interaction is not a restriction on finding the quantum optimization, but the classical one, right? Because otherwise it would be impossible to do the dynamic programming, one dimensional dimension. And then while you see that this mapping of Hamiltonians and inequalities, right, it's not a systematic method, right? So one has to play a bit with that, right? Well, I think that the best way to illustrate that it's not obvious the correspondence is with this fourth example. So this is not solvable with Jordan-Wigner. It's a XXZ model, so it's not integrable, right? And to that we assign a Cézanne's elegant inequality, so an inequality that would look like this. So Alice has 4 measurements and Bob has only 3. Right, and they would be distributed like that in the block sphere. So I mean, they have some nice symmetry and so. And then when you compute the Bell operator corresponding to that inequality, you see that it is actually an XXZ, right? So I have here something that is very asymmetric, that it does not even have the same number of measurements, but it gives me something that is permutationally invariant at the level of Bell operator, right? So it relates to 2 very different concepts. And yeah. And then, well, using the dynamic programming, we can do the same thing, right? Here now we have 2 parameters, the delta from the XXZ and the epsilon, and then the classical bound is piecewise continuous, right? So it looks like this. So I mean, the structure is, of course, much more rich. And well, using these measurements, we obtain this Hamiltonian that is XXZ-like. And the ground state energy of this, you have to find it numerically, right? So here I use some techniques like tensor networks and matrix product states that are very efficient to find the ground state energy of these systems. And then you have a kind of a plot with the non-local region. That would be this one, and the one that you do not detect the non-locality like that, with different number of parties, right? So from 4 up to 1,000, and you see that maybe when this region looks like asymptotically it stays. So let me conclude. So the take-home message is that to show non-locality in a many-body system, you have to solve 3 problems at once. Right? The first one is this combinatorial optimization. You have to find the classical bound, and this we have done with dynamic programming. I mean, you have to show that the inequality is non-trivial, so that actually quantum correlations violate this inequality, because otherwise you are not showing anything, right? And here I showed that one can do it for some systems analytically with the Jordan-Wigner transformation, but in more general systems, you just do it numerically with tensor networks. And then, well, I mean, if at some point you want to test that in the lab, it would be good that it's a bit accessible to the experimentalists, right? So here what we think that is nice is that one measures only 2-body correlators, right? So it's not like other inequalities that have full-body correlators. So this would mean that you need single particle addressing and very high degree of control over your system. Here you measure the smallest amount of information that you can I mean, that is necessary to show that, right? On top of that, if you have symmetries, then everything is much nicer. So you have closed formulas for the quantum value and the speed improvement for the classical one, right? And then, well, this works for any spin system, one spatial dimension and short-range interactions. And from that, well, one can study many open questions. So we think that these inequalities can be more robust, because contrary to the previous works that we did for permutational invariant inequalities, right, in 1D you don't have this definite restriction. So the inequalities should be more robust in this sense, right? And in this work, I have tried to see the Hamiltonian as a particularization of a Bell inequality, but of course one can look it the other way around, right? So I can try to find what is the optimal Bell inequality, because I mean the correspondence between Hamiltonians and Bell inequalities is not 1-to-1, right? Because one can change the Bell inequality, but also the measurements that you use in the Bell inequality, and then different Bell inequalities with different measurements can give you the same Hamiltonian. So because I only need to find the classical bound, right? Once I have the ground state energy of the Hamiltonian, because this does not change, right? The problem is just a classical optimization. So keep changing the measurements and the Bell inequality, and see which gives the best gap, right? And then experimentally, this would be the one that you would use, even if it's very unnatural or very weird or so, but it's the one that has the best resolution. Right, in the fluid dimensional invariant case, this monogamy of correlations is still not clear, or I mean, I think that more studies should be done on that, about how it affects non-locality. And well, a question that I get a lot is, to more spatial dimensions, can this method be used? Then, well, the answer is that the classical optimization, no, because this only works for 1D. But one can do some semi-definite programming and variational techniques to do the optimization. So you can see the classical optimization kind of optimizing over a classical spin system. So there are methods like these chordal extensions and SDPs that can help in this. And then, well, finally, another thing would be this persistence of non-locality. So what happens now? You have many parties. If you lose some of them, right, or you trace out some of them, does non-locality still persist or not, right? And then because there are some states that are, I mean, like GHZ, right? If you lose one particle, you are essentially lost, right? But if you don't lose it, they are very good. But to have something in which that would tolerate losses, right? Then this persistence of non-locality would be something that yeah, also the referees pointed out, and I think it's interesting. So yeah, I would thank you for your attention. Thank the people that financed us, and that's the end of my talk. Thank you very much.
Well, I have a question considering the connection between quantum and classical.
Yeah.
Usually you think that there is some connection, naively we think that it's the value of Planck's constant that controls the amount of quantiness. Now, is there any way here, in your approach, to connect the quantum case with the classical case, choosing some parameter that is present in your model, to make a smooth transition from quantum to classical?
Okay. Maybe that, yeah. From our method, what we have is it's a witness from non-classicality, let's say, right? So I mean, if you violate it, you know that you are non-classical.
Yes, sure.
But if you don't violate it, then you could still be non-classical, but you could not be able to detect it with this, with our witness. So this is smooth transition. I'm not so sure if this could be done, right? Because it would need something that would be a kind of if and only if.
We know that classical physics almost works, except in cases where it doesn't work. So there should be what was called correspondence principle. Is there a correspondence principle here involved that gives you the connection between the classical mode and the quantum mode? For example, if you take very, very many particles, you approach them classical limit.
I mean, well, there have been some principles that people have put.
At some point that the violation is small, that it's a certain number.
Yes.
No? And this, of course, is a dimensionless number.
Yeah.
So this should depend on some dimensional parameters.
The question is now, what is the difference between the speed 1/2 quantum mechanical and Isaac speed? And that
Easy.
Isaac speed. And that's basically the difference. Where I mean, they both have, right?
Okay.
That's the fundamental thing. Right? And for classical model, I mean, I can write the same classical model. The only question is that the Jordan-Wigner transformation will not work, and the H sits in this transformation because the limit is that the classical limit is that the couplings between the energy of the coupling times the Planck constants must go to the final value. So this, I mean, there were never these coefficients written, but if they were written, we will see what happened. H goes to 0, but the energy must go to infinity, but the product is fine.
Questions, you think again?
Thanks.